Welcome back. I hope that you had a good break and managed to get a drink, and hope you're ready for our next panel of the day. So our first panel explored some really big ideas considering how our engineering community and education system and policy making will need to change to enable us to meet net zero. We're going to take some of those ideas and consider what they mean in practice within one very key sector, the built environment. And we'll explore how we can make sure that our homes and our workspaces and public infrastructure are moving towards being carbon neutral. So for this discussion, we are joined by three speakers from Ireland, France and Belgium. We've got Professor Brian Norton, who is Head of Energy Research at the Tyndall National Institute, Research Professor, University College Cork, and Professor of Solar Energy Applications at TU Dublin. Brian recently chaired the work of the European Academy Science Advisory Council that led to the major 2021 report on decarbonisation of buildings in Europe. Our second speaker is Dr. Maher Chebo, Director General at Accenta, leading the company's innovative work focusing on low carbon technology and AI solutions for buildings. And we've also got with us today Professor Lieve Helsen, Professor in Mechanical Engineering at KU Leuven, where her work focuses on optimizing thermal systems to provide low carbon services in the built and industrial environment. So to kick off, just like the last session, each of our panelists will give us a 4 or 5 minute view on the topic, and then just to let you know, speakers, if you are running out of time, I may cut you off, so please don't be offended, but I want to make sure that we have lots of time for questions, and I will leave more time for audience questions this time. So apologies if your question didn't get answered last time, but I'll try and get through all of them now. So I'll start with Brian, please.
Thank you very much, Yasmin. Yeah, decarbonisation of buildings essentially comes down to two things. It's reducing the energy use of buildings and then meeting the residual energy use by decarbonised sources of energy, which tends to be decarbonised electricity from renewable energy resources, or, for example, heat from district heating systems. So in simple terms, it's an easy thing to say how to do. The problem is, and this came out of the European Academy's study, is there's no single then solution on how to achieve those goals, no single silver bullet. In new buildings, there's a strong thing around new building regulation, etc., which throughout Europe has increased building standards, and indeed the achievement of highly rated buildings and net zero energy buildings or near zero energy buildings for new buildings is indeed achievable. But the challenge is new buildings are only a tiny proportion of the building stock, and it is existing buildings, the refurbishment and renovation of existing buildings, which is the major challenge, and that varies throughout Europe, and it varies throughout aspects of the building stock depending on the tenure of that stock, whether it's owner occupied, it's social housing occupied by private landlords, and there are divergences between the benefits and who pays the costs in those situations, which present barriers. Among the challenges going forward are issues to do with how buildings are rated, and I can discuss that in more detail. In terms of introducing energy storage into buildings, because they still have this problem of winter peak electricity loads and more interseasonal storage so that the overall system is more efficient. Issues to do with indoor air quality, particularly brought to the fore in our present global pandemic, where you don't want to reduce indoor air quality from a health perspective, but from an energy perspective, one seeks to reduce air change rates and have waste heat recovery, etc. So there's some optimizations there. The big issue in refurbishment of buildings is that there is energy embodied in the actual refurbishment, and so one's seeking to reduce energy consumption, CO2 emissions, but there's a whole lot of energy embodied to do that refurbishment, which is effectively paid back by the operational energy savings. But in the short term, actually energy increases. So there are issues to do with how materials are rated, but also there are design choices in terms of buildings that need to be taken. And finally, there are a whole lot of issues to do with how the refurbishment of existing buildings is actually financed to be affordable, because there is a public gain in terms of reduced CO2 emissions, my wider social gain, but there's also a private gain in terms of lower energy bills. And some of that also leads to things like rebound effects, where people might take higher comfort temperatures or greater lighting because they can now afford it. But there are other groups, and it's again varies in different localities and different countries, who spend more than 10% of their disposable income on energy, and existing energy poverty, for whom affording these particular measures is simply impossible. And often they're in rented accommodation, where the benefits don't obviously go to the landlord, who's going to pay. So there are big social issues in terms of the refurbishment of existing buildings. I'll stop there, and maybe we'll pick on some of these issues and questions.
Thank you very much, Brian. Maher, do you want to go next?
Thank you. So why buildings decarbonization is so important? So buildings, they account for 27% of the annual greenhouse gas emissions. Heating and cooling, that represent about 55% of what a building consumes, they account for 10% of the GHG emissions. So the mission is to kill about 5 billion equivalent CO2 per year, and to bring it to zero if you want to decarbonize the whole buildings. So why is that important? What's the risk? If you have a building which is not good in terms of carbon emission, it's not low in terms of carbon emission. So you have social challenges, you have legal challenges, you have exploitation challenges, you have profitability challenges as well. And you have a risk of the value of the building that you have. If it has a high carbon footprint in the future, its price will not be the same as another one, which is highly designed and sustainable. So we have worked on a solution that started at the prestigious institution called Polytechnique in France, on a model that the scientists have developed to size and to monitor, with the help of the artificial intelligence, a building which could be low carbon based on geothermal storage. So you would take the waste heat, for example, from air conditioning, you would take the excess of solar heat during the summer, you will store it through tubes where you put fluid down to like 100 or 200 meters under the ground. And then you can recover when you need that energy. You can recover it only almost 100% during the winter when you need to heat, for example, your building. And that solution can help you cover 100% of your cooling and heating HVAC requirements. The headquarters of the Airbus in Toulouse is 100% covered by this technology. And that technology can contribute to like 93% of lower carbon, 14 times less than classical solutions, for example, that we have. Of course, there is a number of renewable technologies. So if you have a building where you have solar PV, not only solar thermal, we can size the building in a way that you have a good multi-energy renewables from solar, from geothermal storage, to cover completely the needs of the building. The solar PV will be producing clean electricity. That clean electricity is useful as well for the heat pumps. And at the same time, it's useful for lighting and for electricity. The impact of these kind of technologies, when we are talking about decarbonizing or low carbon buildings, or reducing the carbon emissions by more than 90% and having an energy efficiency of 70% in Europe, that has a huge impact on about 50% of the emissions that we have in Europe. So we should also look at acting on demand. So here what I'm talking about is producing clean energy from geothermal storage. So acting on demand means putting in place technologies where you can remotely, with the help of the artificial intelligence and machine learning, act on the heating and cooling systems, smart building energy management systems, and these could contribute to 10 to 40% energy efficiency on the building. So we need to look at both technologies, the one acting on producing a clean energy, actually producing is we are recycling wasted heat and solar abundant and putting that, storing that with geothermal storage, and acting on the demand, which contributes 10 to 40% energy efficiency. Both of them would contribute to high results in terms of energy efficiency, which could be 70 to 80%, and decarbonization about 90%. Now, I would like to let you with 7 recommendations we have put in place for scaling up and the massive low carbon buildings. First is, here we are talking about cross-sector coupling. So we need science that looks at the building architecture, building engineering systems, data, digital, artificial intelligence. We have many sectors that are involved. So sector coupling is something we need to keep in mind. Second is we need to explore best-in-class physical and software technologies that could be used for the envelope, because some people would work on the renovation of the envelope, even if the renovation of the envelope could cost 5 times more than the geothermal storage, and have 3 times less return on investment. So we need to look at the best-in-class technologies still for the envelope and still for the energy systems that we are talking about. Third, we need to be completely mindful of the fact that the data is the nerve of the war. You cannot make any diagnosis on any building to be renovated or to be improved or to be more low carbon if you don't have data on that building. So we need to work on having like a data hub, 360 degrees, which includes the consumption, weather conditions, includes some economics, and includes data that is helpful for the life cycle of the building. And then we need to work on service level agreements. Today, the buildings are static. We need to consider them as a life cycle, from the design, in construction, in renovation, in putting in place new energy systems, low carbon energy systems. We need to follow all of that through service level agreements, and then jump into outcome-based financing. A lot of people are not capable to finance these projects. So there are more and more fund managers, organizations that put in place funds that are available for financing completely these projects and get remunerated on the savings and on the decarbonization. We call it outcome-based finance. And finally, scaling up means that we need to look at 2 dimensions, either buildings sitting into a district at a geography where are close to each other, typically a campus of a university where you have 30 buildings, or a district where you have several buildings that share the same land. And we need also to look at the organizations that have a diffuse fleet of buildings. You take a postal company in France or in many other countries, they have 10,000 buildings. They have millions of square meters. These ones who need to decarbonize their buildings, they need to have a view, diffuse, consolidated at the top level, exactly as you consolidate your finance or P&L, you need to consolidate also your emissions at the top level. So there are solutions that are capable to do both, look at the geography or eco-districts, for example, side, and also looking at consolidating buildings that are diffused across the whole territory. Thank you.
Thank you very much. And over to you, Leva, please.
Thanks, Yasmin. I would like to start by stressing the urgency in the built environment. Given the lifetime of technologies installed, action is needed now, today. And we all know the technologies exist and the trends are clear as well. We move on the one hand towards electrification by using heat pumps, but also towards collective approaches by using thermal networks. Of course, we have to make a distinction between renovation and new buildings for sure, but for both categories, system integration is key. So my first statement is it's time to move from a technology readiness level, a TRL, towards a system readiness level, an SRL. And let's start with renovation, which represents the biggest market share. We should aim for an optimal combination of the building envelope and the energy system. So using the full potential of the building to reduce demand and fit this to the HVAC system and the controller, and thereby progressively increasing the share of renewable and residual energy sources, not only to mitigate climate change, but also to improve the air quality and autonomy. Now, when the budget is limited, which is usually the case, then, and the full house option, let's call it, is not feasible, then future-proof design and flexibility should be points of attention. So typically hybrid systems where less efficient or fossil-based technologies keep a minor part, they can deliver the major part based on the renewable energy sources and in a cost-effective way. Now, which systems have to be installed? That's a big question. And to compare different alternatives, dynamic simulations are needed. And this represents an extra engineering cost. So my second statement is a cost-optimal design fee is only that one that leads to a cost-optimal project, where cost includes all externalities. So we have to care for people and planet as well. Now, maximum integration of renewable and residual energy sources requires low Exergy systems and hybrid systems. And dynamic simulations allow a correct evaluation of hybrid system concepts and their control, which both can have a huge impact not only on the energy we need, but also on the power we need, and thus on the global system performance and the total cost of ownership. Now, since it's not easy to realize that 100% renewable energy sources based on individual building level in a cost-effective way, we have to look further in space and time. And by moving towards smartly controlled collective systems, a synergy can be exploited. And then the question is, at which scale do we have to look? In Belgium, we are not that collective thinking yet. So there, maybe we have to start from very tiny clusters, for example, 3 neighbors that share their energy system, and then gradually moving to larger neighborhoods where system integration becomes then a real challenge in both operation and design optimization. And taking into account the current trends towards electrification, smart grids, exploitation of flexibility, I come to my third statement, which is buildings have a role to play in the global energy system. Now, if we move to new buildings, it's clear that design has much more degrees of freedom, and system integration can be realized over timescales, over technologies, multiple buildings, sectors, and thereby including the local context. And a nice example here is the hybrid geotapes concept. Within the hybrid geotapes concept, a heat pump is used. So there we introduce energy efficiency and electrification. The source is typically a bore field, but depending on the local context, it can also be an aquifer, a sewer, or something else. This is renewable energy source, and this allows for seasonal energy storage and also for direct cooling. At the building site, the heat pump feeds then taps. Taps are thermally activated building structures, and they are a low Exergy heat and cold emission system, and they represent the short-term storage. So they allow the interaction with the smart grids through demand response actions. Now, since each building deserves a geotap system and architects need their design freedom, we add a fast-reacting secondary system to cope with fast disturbances, so we result in a hybrid system, and that needs smart control. White box model predictive control is then the whole system integrator, where we can optimize towards minimum carbon dioxide emission, maximum share of renewable energy sources, or minimum energy use or cost. So hybrid geotaps is a very strong concept for climate neutral comfort supply, where MPC is the system integrator, and MPC can improve comfort and at the same time lead to energy savings up to 40%, as we have shown in demonstration sites. So I would like to conclude with my final statement. In hybrid systems, design and control are challenges, but both influence each other, and this can be maximally exploited towards a cost-effective synergy on building level and on cluster level. Thank you.
Thank you very much, everybody. I'm going to start with a question that's come in through the Q&A. And just again, to remind everyone watching, please do submit your questions at the bottom of the screen. So everyone is talking about making the building environment sustainable. What about the carbon footprint of creating the building in the first place? How do we use less steel and concrete, which are very high carbon? Who would like to take that first?
Maybe
Right.
I'll start. It is, as I said, an important issue to look at the embodied energy of buildings. And one thing is actually to focus on refurbishing rather than building new buildings and see if you can actually reutilize buildings. But it comes deeper than that in terms of actually designing the components of a building so that they are available not just for recycling but actual reuse. So design for reuse, designing systems so that the components that are most likely to fail, and things do fail inevitably, but you can predict the failure of things, and the components that are most likely to fail are designed to be replaced. So there's a whole set of issues around that sort of circular economy to minimize that impact, and using much more of the materials that have high energy content because they're production processes are essentially available for reuse at the minimum would be the key challenge.
Thank you. Maher, did you want to comment?
Yeah, absolutely. So the whole life cycle of the building counts, and everything that you need when you are at the construction level and even at the renovation level. On the envelope, you have a number of materials that you use that have a carbon footprint, and all the models that are the true ones or the most accurate ones include everything in the carbon footprint, in the material you use for the envelope, in the emissions of the building as well, with the energy system that you have in place, the gas. If you have gas boilers, you will also calculate the gas boilers and so on. Now, cement industry contributes to 15% emissions in the world. This is a huge, okay? And if you take a company like Lafarge Holcim, they have a whole team working on reducing their emissions with new types of materials, for example, that could be used. If you take a company like Vinci is a construction company. They have now a kind of an envelope they put on the surface of the buildings that integrate what we call BIPV, building integration PVs as well, that are in the same time producing electricity. All of that is calculated in the emissions. And this is why what I said is we have to look at the investments. If you have, for example, 60 euros to spend for the British pounds, then where would you spend it and what's the best return? Would you spend it on an envelope that costs a lot of money and then gives you some return, for example, maximum 30 or 40% energy efficiency, or would you spend it on the energy system that would cost 5 times less and give you 3 times more return on investment because you can have 70% energy efficiency and 90% decarbonization? All of that is calculated with Excel sheets simply. And then you can get to the best result just on calculating and putting everything. You should not have any hidden cost or hidden footprint of CO2, and the models are good today.
Thank you. And Liva, did you want to comment on that question?
Maybe very shortly. I agree that you have to look at an holistic approach, that you have the complete life cycle cost for the whole system. But I also want to stress that you have to match the building with the energy system. That it's not just choosing the building envelope and choosing an energy system and then, okay, they just have to work together. They really have to be matched. So I think that's important as well.
Yeah, just to say, yeah, there have been calls, for example, from the Green Deal around the whole matching actually of the building construction or renovation and the energy systems. We have been working with like 20 partners to make that match, construction ones, energy systems ones, digital companies as well, companies that are specialized like Viscap, for example, into calculating the overall life cycle of carbon emissions for a building. And the objective was to make all that match to reach out at the end, less cost on the construction side or innovation side, less energy consumption and less CO2 footprint, all combined and all integrated in the new approach. Today, they are not integrated. You are right.
Yeah, I think we did talk quite a bit about collaboration in the earlier session, so that comes into here as well. I'll take another audience question. The carbon emissions of buildings are being noted in discussion, but these are usually modelled and often using quite simple models, and for example, EPCs. How can we use real data to inform our decisions on carbon reduction and do so at scale? And I think maybe, all right, go to Brian first.
I'm happy for someone else to go if you wish.
I was going to go to Maher just from the kind of AI perspective, but you go first, Brian.
Okay, I'll
give him a chance to think.
Yeah, well, as I started, I mean, it is a very important area because a whole lot of national policies are based on supposed national energy consumptions of buildings, and yet no country actually measures the energy consumption of all their buildings. So those numbers are actually based on EPCs, energy performance certificates, and they are a rating of a building for a defined type of construction, occupancy, heating system, etc. And they are not designed to correspond to actual energy use for each individual building. Now, the theory is they do in aggregate, but many studies have shown that's not actually the case, and it's not actually the case for older buildings. And that leads to a whole lot of issues to do with the effectiveness of policies when they're actually introduced, interventions when they're actually introduced, and also the expectations of policymakers as to what energy savings that might actually occur when you make certain interventions globally. And that's further compounded by the fact that buildings are not systems, they're not energy systems, they're systems for people to be in comfort and health. So the objective is people, and people rather than energy. And if you insulate a building, for example, people will take higher comfort temperatures. If you have low energy lighting, and the modern LED lighting, for example, uses a fifth of the energy of an incandescent bulb, but you tend to have more than 5 times of them. So you've got more lighting energy, and those things need to be factored in as realities rather than inconveniences into the process. So, picking up the point that Leva made, I think a big thing is to have much more detailed simulations of entire stocks, so that and validating those simulations with comparison with actual measurements, and then a whole lot of other things using AI, which others could talk about around how you use that data effectively.
Thank you.
Yeah, I mean, today, as I said, the nerve of the war is the data. We spend much more time into collecting the data and knowing what is the baseline of the current building, what is the building consuming, where is the building consuming, in the lighting, in the electricity, in the heating, and so on. And if you don't have the meters in place, well placed, all the sensors in place, you do not have all the detailed data that can help you make the transformation properly. So the starting point is to make a diagnosis, collect data. If the data is not available, is to put sensors and to collect that data through sensors. And then you have also international references like the IPMVP, International Performance Measurement and Verification Protocol, that helps you comparing apples with apples. So the current referential, for example, when you measure it with the IPMVP, you know afterwards, you know, what does it mean to improve it and to have 20% energy efficiency on it or 50%, and compare on a yearly basis how much improvement you have been making. Okay, so today when we make the calculations regarding the CO2, we know exactly the carbon emissions for the gas. We know exactly the carbon emissions that are calculated country per country from the electricity. In France, the majority of electricity is clean because it comes from nuclear. In China, that would be a different story. So we calculate that properly as well. And then if somebody has also a plan to change gas by biogas, we know also that the biogas has like 70% less carbonization than a normal gas, even if the price is higher. All of that is calculated in our economic calculations to say, what does it mean if I do that project in terms of transforming an existing situation with its referential to something which is better and more energy efficient. One KPI is the energy efficiency. Second one is decarbonization. Third one is the cost. And the last one, which was mentioned by Brian, is the well-being. It's very easy to have an energy efficiency or reduce energy consumption if people, you know, get a bit colder, but we don't want them to be colder. We want them to be at the same comfort. So at equal comfort. So the well-being is part of the story as well, and that's an important KPI beside all the 3 KPIs I mentioned before.
Thank you. And Liva, did you want to comment on this question?
I would say it's the core KPI. I think we do not build to use energy. We build to give a comfortable indoor climate. That's the main reason for buildings. Now, I want to stress indeed that measured data are extremely important, but what we in research encounter is when we test, for example, our advanced controllers in the real buildings, that the data we gather, they are often corrupt, or we have missing data. So the whole story on big data, I'm really willing to believe that's the way to go, but then we have to do something on the way the sensors are installed or the quality of the sensors, because what we now see is that a lot of rubbish comes out, and that's not something you can build on. So this is really a difficult point today still. We are not yet there, I would say.
Thank you. I've got a sort of related question. In the last session, we talked quite a lot about behaviour change and how we bring everyone that's involved in the energy transition along with us and engage the public. And I think that obviously applies quite a lot here, as you've all just said. How do you think we can deal with this as engineers?
Yeah, I mean, in the behavior change, it depends about whom we are talking. I mean, if you are talking about users and asking the users to be smarter, this is what I heard, for example, when we co-founded the smart grids in 2005. People were saying we need to have smart users. No, that means we failed. If we need the user to be thinking about everything every day, we need the technology to help the users by sending awareness, by sending alerts, by doing a lot of things that are automatic or semi-automatic, that we get to the results that we want to achieve. But we should not just consider that the users have to be absolutely smarter to be successful. Then the other behavior is the way we consider the real estate of buildings today. Today, you have the ones who build the buildings and they don't care about what happens afterwards. You don't have any life cycle. You have people who exploit the buildings who are different from the ones who build them. So you have everybody like is giving the hot potato to somebody else, and take care. It's out of my business. We need to change that. We need also to make sure that all the ones who provide numbers and say, yeah, no worry, I will get your data, I will put my technology, you will get 20%, and at the end, you don't observe 20% energy efficiency. So you need to have a skin in the game. You need to have people who really present technology solutions, provide economics, and take commitment on the performance. There are contracts for which there are subsidies. If you have a commitments on performance and decarbonization, you get the subsidies related from the government to that. It's what we call in France certificat d'économie d'énergie, for example. And if you don't get to that commitment on the performance, you don't get them, or you get much less than the ones that you ask for. So these are the things we need to put in place. And the last point is the financing. Yes, to make transformation, you require a CapEx, and then you have an OpEx. To get an OpEx which is cheaper, which is better, and so on, because you have put in a certain technology in place, you need to invest sometimes more. We need to simplify the financing models and make that like a common practice in public as much as in private. So traditionally, you can do it in private, for example, but not in public. So we need to have that in place in both. And then allow that, between the first time where somebody says to you, I want to decarbonize my building, and the time you start the project and you get it live, you should shorten that time to a maximum by having these standard models of financing and get remunerated on the savings.
Thank you. I'll come to you next, Liva, because you've made quite a good point that we build buildings for people's well-being. So I don't know if you have any views on behavior change, or how we engage the people in those buildings in this?
Yeah, it's a difficult one for engineers, I think. So I would rather put a warm call to collaborate with human sciences, because I think we as engineers, we will not solve the whole problem there. We really need that expertise as well. And then we can develop technology that makes that it's like almost automatically done. That as first we need to know the preferences of the user and how the acceptance can be increased and so on, and then we can adjust the technology such that the users themselves do not have to be concerned about it, that it's just going on and yeah, in a quite automated way. I think that's important.
Thank you. Brian, did you have any?
Yeah, I think the problem with the built environment behavioral change is whose behavior. And we tend to think maybe the responsibility of building occupants, but the behavior of builders, that how they build buildings. For example, there's a tendency in some jurisdictions to build new buildings, or indeed where there are standards in place, refurbished buildings, to the minimum standard. And yet there is very little cost penalty in building beyond that, for example. So there is behavior there. Often people are in social housing or private tenanted housing, and it's the behavior of the landlord in terms of their responsibility, etc., that needs to be developed. Underpinning this is, I think, a more fundamental issue of the public and private benefits, in that there's a public benefit in reducing CO2 emissions, in security supply of energy use, etc., which has to be taken, I think, as a collective burden on society, and then provides the incentives that create a different playing field for private behavior. Also, more fundamentally, and at the building physics level, but one of the challenges with low energy buildings is actually in many climates they overheat in summer. It's very easy to develop a building which is energy efficient from a heating perspective, but you've got an overheating problem. You've seen that then arising major problems of mortality due to overheating of buildings in the summer. The solution to that is that building fabric elements, building facade elements become more adaptive to climate. So there's not just one point of equilibrium, in the year, and then either end of that you need heating and cooling, and that then gives the occupants of a building more opportunity to adapt their building to the climate. And I think the opportunities for people to modify their behaviour in terms of the operational use of buildings are limited at present. So there's a lot of dimensions to that question.
Thank you. Let's take another one from the audience. I think we've talked a little bit about this already, but could we have your views on whole life carbon assessment in the built environment? Is this a useful step to understand our current emissions and help guide us to a decarbonised building sector? And what else should we be doing? Liva?
I would like to make a main comment in the sense that we often talk about carbon and carbon dioxide and sometimes greenhouse gas emissions, but there are much more pollutants than that. So I think local pollution is maybe as important as global climate change is, and we should consider them all. I think if we go to a life cycle analysis, life cycle cost, we should include all ways of environmental pollution and not only climate change. I think it's an important challenge and we have to go in that direction, but we should not forget the other things. And I think good databases are important to rely on to get all these calculations, and I think, yeah, it's the way to go to make this holistic approach. Yeah.
Thank you. Brian, did you have a comment?
Well, I would agree totally with what Liva said. I think the important thing is not just to do that assessment, but actually build it right back ab initio into the design process, whether that's a new build or a refurbishment, etc., as part of the design process, because it's not just materials choices, but actual design choices. We don't have time to go into detailed examples, but there are design choices which can lead with exactly the same operational energy saving, operational reductions in pollution, but have much less embodied energy and much less local environmental impact.
And Maher, did you want to make a quick comment on this one?
The air quality is more and more requested together with the request about the energy efficiency and decarbonization. And this is why, for example, Axanta has been acquiring recently a company that includes air quality, for example, in their solution. We work also with a partner in China, which is a joint venture with between RN and Aden Group. And in China, they have developed also a platform together with the energy efficiency, which includes, of course, air quality, which is an important topic there in terms of pollution. Same for India.
Thank you. There is a question which I think is off the back of the work you described, Liva. Are there plans to extract heat from the heated waters in the sewers downstream of the buildings?
Yes, there are plans to do that. Indeed, we are looking how can we use the local context as much as possible and as good as possible, because not only extract things for our use, but also safeguard the nature itself. We should not harm these local resources, and how can we include them as much as possible into our global system approach to heat, cool, and ventilate buildings, and make it happen across the borders of one building. So usually this encounters the infrastructure of a thermal network, and often it's just a low temperature thermal network where we just use the temperatures as they are available in nature, and we upgrade them at the location where we need the heat up to the temperature level we need. As such, we can have a very good match in what we then call Exergy instead of energy. Yeah.
Thank you. And is that something you've come across in France or in Ireland at all?
This is a fantastic opportunity. We traditionally use for the geothermal storage the waste heat coming from air conditioning and excess from solar. We believe this is also another opportunity for what we need to store at a certain temperature at 100 or 200 meters, where we need like 12 degrees. And that's really a fantastic opportunity as well to get the thermal storage and to use it when we need it.
I think this is all part of a wider agenda of sort of intersector coupling, of matching your energy sources to your energy needs. I don't think there's waste heat recovery in that context in Ireland at present, but there is, for example, projects where district heating is using the waste heat from data centers, for example. And that idea of looking at proximity and looking at from a systems perspective, and look at the opportunities for intersector coupling both with heat, electricity, etc., is, I think, crucial for the future.
Perfect. Yes, Liva.
Maybe to mention that it's not all I would say very easy to implement, because the main challenge in that system is the heat exchanger. It's fault immediately. So you need systems, you need innovation on the component level that cope with this. But energy-wise, it's a good solution.
But this is why it's important to look at things in a holistic way. If we work in silos, take the example of electricity and heating, for example. If you take the electricity side separately and the electricity storage separately from the thermal storage, for example, you might not be optimal here. So you have to put it together and then work on the storage both sides, flexibility thermal as well and flexibility electric as well, and make them all work together.
Thank you. I'm afraid oh, sorry, Liva. I think we can have one final comment, but we are out of time.
Yeah, I'll make it short. I have the feeling that we see that a lot of technology exists, and it's the main challenge today is putting everything together and let it work together in a good way, in an optimal way. And there often funding agencies feel like this is not innovative. So if you want to apply for funding for that type of research, they say it's just combining things that exist. What's new? And I think they feel like everything is there, But making it work together, it is quite a challenge still today, and that is not yet solved if we go across sectors and so on. So there is still some work to do there, and maybe we should stress that a bit more, because policymakers often think it's all there, and there is still a lot to do.
Yeah, if you look at the Green Deal Innovation Fund, where the European Investment Bank has put some money to fund decarbonization, big industrial decarbonization projects, they consider that putting things together and the integration as innovative, even if every component of that system is not innovative, but the assembly of all of them, they consider it innovative, should be around TRL 9 to be eligible for a Green Deal Innovation Fund, whether it's large scale or small scale. So you are absolutely right.
Yeah, but then you talk again about a TRL 9. I really want to push to go to an SRL. We really have to go that whole chain as well. We are indeed at the higher end of the TRL, but the SRL, we are still very low level.
So they still use TRL as a terminology, but they consider the system to be innovative overall. So they don't call it SRL because that's not a terminology commonly used, but they accept that people come and have plenty of like electrolyzer and plenty of things that are available at that work, but they have never been integrated all together as being an innovation. And in this case, they say it's fine, then let's put a good score also for the innovation on that project. Sorry, Yasmin, for taking more time.
No, it's a good point to end on. I think it ties into a lot of the stuff that we were talking about in the earlier sessions around collaboration and systems thinking. So thank you very much to all of you. We will. That's the end of the session for this morning. There's lots of us to consider over the lunch break. So I would like to thank all of the speakers who have been with us over the course of the 2 sessions this morning for the really insightful contributions that they've given us on these topics. Our session for the morning focused on Our sessions this morning, focused on a topic that's widely acknowledged as the cornerstone of building back better. Following our recent COP conference, we are well aware of the urgency of building a more sustainable future. And I think we've had a brilliant discussion this morning about what that could look like in practice and how we as the engineering community can help to deliver it. This afternoon, we are going to be exploring a slightly different topic, which is perhaps less prominent in our news and social media, but very essential to delivering a more sustainable future. And that is all about how we build resilience in our complex and interdependent systems and in the world. So please join us again for that session. We will be starting again at 1:45 UK time, which is 2:45 Central European time. In the meantime, I hope you enjoy your lunch break and get a chance to get some food and hopefully step away from your computers and maybe get outside if it's nice and sunny outside. So please be ready to join us again at 1:45 GMT. I will see you then.